Hello everyone, welcome back to your YouTube channel and welcome to this amazing video today. As you must be aware, I am recording this series of videos related to electromechanical conversion devices. And the reason is my students, my amazing students, they are taking this very exciting module. So I am recording this practical example, this numerical calculation for them. And one very important aspect when we are working with electrical machines is the induced voltage. And for that reason, today we are dealing with this very simple but exciting and useful example. Let's start here reading this statement. Consider a rectangular coil of sides 12 centimeter and 8 centimeter and is rotated in a magnetic flux density of 1.4 Tesla. The longer side, that means 12 centimeters, of the coil actually cutting these flux. The coil is made up of 80 turns and rotate at 1200 revolutions per minute. And now we have here two very exciting questions. And question A, calculate the maximum generated electromotive force in volts. And question B, if the coil generates 90 volts, what linear speed V in meters per second will the coil rotate? So as you can see, the situation is depicted over here, is shown over here. We have this square coil. You can see that the longer side is L and the small side is D. And this is rotating inside this magnetic flux density that I use here this blue arrow to represent. So let's start the solution. As you must be aware, I am using the classical MATLAB live script. So as a consequence, I need to input this data. So I will start with this command over here to clear all the variables, and then I will define the longer side of the coil, and this is 12 centimeters, but I am including 0.12 meter, that is the conversion from centimeter to meter. And over here you can see the same. Now we are using 8 centimeters. When we are talking about meters, this is 0.08. The magnetic flux density, you can see 1.4 Tesla. The rotational speed in RPM, 1200 or 1200. And the number of turns, 80. Well, I believe all my students know this equation number 1 located over there, because these equations say that when this coil is rotating inside the magnetic field, between those two terminals over there, we will have a electromotive force or induced voltage. And this induced voltage will be dependent on twice the number of turns of the coil, the magnetic flux density in Tesla, the length of the segment of the conductor segment cutting the flux line, the velocity of the conductor, but be aware because it's meters per second, and finally this angle theta that represents the angle between the conductor and the magnetic field. So now we know the equation that we should use. However, there are some conversion here related to units, because as you can see, the rotational speed is 1200 RPM, but inside the equation we need to use meters per second. So to convert that, what we need to do is basically what we need to do is uh, basically what we need to do is take the RPM, and first there are 60 seconds in 1 minute, so those minutes cancel each other. And now this revolution must be multiplied by the total length inside the revolution. So when this coil is rotating, well, the radius multiplied by 2 pi, that is the total length of the circumference over there. So we are multiplying 2 pi radius, but the radius is equal to the diameter divided by 2. In other words, we are multiplying 2000 RPM, 1 divided by 60, 2 pi, and the radius in this case is the diameter divided by 2, 4 centimeters. So you can see here on the right hand side, we have the result, numerical result for the speed, and in this case is 5.0265. Now, as we are asked about the maximum induced voltage, the maximum induced voltage, the maximum induced voltage is produced when the coil is located at 90 degrees, or in other words, where the angle theta is equal pi half, and in that case is radian. So now is a basic numerical substitution in the equation number 1. We have here 2, the number of torque 80, the magnetic flux density 1.4, the length 0.12 meters, the rotational speed that we calculate early, and that is 5.02 meters per second, and the sine of theta. So finally, as you can see over here, when this square coil is rotating at 1200 RPM, the maximum voltage induced over there is 135.1 volts. So we got the answer for question A, and now what we need to do is go for question B. And if on question B, we know that the induced voltage in that condition is 90 volts. So we want to obtain the linear speed. In other words, we want to calculate this letter V here inside the equation number 1. And what we need to do is extract the letter V from this equation. So extracting the speed, you can see that it will be the induced voltage divided, here in the denominator we have 2 and BL sine of theta. So now is just question of the substitution. Remember, the induced voltage is 90 volts, the number of torque 80, the magnetic flux density 1.4, and you can see 0.12 meters and sine of theta over here. So when we produce the numerical result, you can see that the answer for question B is 3.34 meters per second. So this is the answer. However, I want to go the extra mile, converting those meters per second, converting these meters per second into revolution per minute. And to do so, what we need to do is basically multiplying the meters per second by 60 seconds in 1 minute and dividing here 2 pi the radius. So after the numerical substitution, we obtain over here the rotational speed now in the units of RPM. And as you can see, the result is 799.3 RPM. So it's very important that when you finish your calculation, reflect about the results. And as you can see over here, if the coil is rotating 1200 RPM, the induced voltage is 135 volts. But if we decrease the rotational speed to 799 RPM, well, the induced voltage will be 90 volts. So as a consequence, it's very simple to see, all my students, that the rotational speed has a very important effect on the induced voltage. And in this example, we realize and clearly demonstrate that. Well, we are almost finishing this example. This example was related with the induced voltage of one coil that is rotating inside a magnetic flux density, a very important topic when you are working with rotating machines. And before we finish this video, I would like to invite you to be part of our community. And here you have the link for our LinkedIn connection. We are updating quite frequently the status and providing a lot of information. Also, I invite you to subscribe to the channel because they are very important videos for the members, and also you will receive update about the videos. If you want to know more specifically what we are doing in development, research, and innovation, please go to the Twitter account or to Instagram, and please feel free to follow us. Well, this is the very end of this video. I hope that you understand the explanation, that you enjoy the explanation, and also that this knowledge will be helpful for your future. If so, please remember to provide a like or also to give or leave a comment. Well, this is the end of this video. Thank you very much for watching, and I will see you at the next one. Bye.